Okay. Um, Thanks. So, first of all, I would like to thank the organizers for inviting me to present our work. So, I'm going to talk about constraining abundance of primordial black holes using Subaru HSC data. A lot of my collaborators are listed below, but I wanted to highlight a couple of them. Hiroko Nikura, she was a PhD student. She used to work at IPMU, but registered at the University of Tokyo. So she did a lot of the work. And then Masahiro Takada, who has been the brains as well as the force behind some of this work. Um, so a lot of this work was done when I and Anuprita, both of us were at Kavli IPMU. So that's why the double affiliation here. Let's begin. I don't want to go into too much of introduction. Of course, we know that dark matter could be made up of primordial black holes. The nature of dark matter is still a mystery. So there are many, many theories around. And so we would like to constrain the nature of dark matter. Um, of course, observations are really, really hard. And so I'm trying to give you a status of where observations stood before we carried out our Subaru observations. So this is a plot that you're by now very much used to. This is omega PBH by omega dark matter. So what is the fraction of dark matter which could be part of, which could be made up of primordial black holes? And then you're seeing these different kinds of constraints, some from CMB, some microlensing constraints from Kepler and Eros. Then there's the black hole evaporation constraints and femtolensing constraints here. So this was kind of the state of the art at that time when we began things. Of course, now we know that the femtolensing constraints may also be dubious due to finite source size effects and so on and so forth. So there is a big window which is open here. And we wanted to see if we can address, if we can design some observations in order to constrain that particular part of the mass window. Of course, it is a two-edged thing, right? Either you can constrain the scenario, or maybe you would be the first ones to detect something like that. So that was the aim, and that's where basically we began, right? So wanted to observationally place some constraints in this particular mass window. Just to orient you in this particular plot, the mass of the moon will be somewhere here. So at roughly, if you times 10 to the minus 8, right? And so it's even smaller than the mass of the moon, right? So these are the kind of ranges that we are trying to address. These kind of primordial black holes, if they exist, they will be extremely tiny. So the observation probe that we are using is gravitational microlensing. So just for students in the audience, what happens is if there's a star, there's light coming from the star, it reaches you on the Earth, and then you can see this particular image of this star. So if nothing is happening, that's all you see, the image of the star. But you can imagine that maybe there's a black hole which also wanders by and comes right in the line of sight to this particular star. In that case, due to gravitational lensing, you can have multiple paths that these different light rays can take and reach you on the Earth. And what happens is that you see, instead of seeing one single image of the star, you now start to see multiple images of the star. So that's gravitational lensing for you. So of course, as time goes on, if the black hole moves away, then you again start to see the star as you should be seeing in the absence of this black hole. I personally work on gravitational lensing, and many a times I have to deal with images which are coming from different directions, so we can resolve these images. But the particular case that we will be focusing on today is when the separation between these images is so small that you cannot resolve it with your telescope. So in that case, what happens is you have these multiple images, they merge together and give rise to something called a microlensed image, which you can see here in the middle panel. And so what you see is that there is a star, its light or its brightness just goes up, and then it goes down again as the black hole passes along the line of sight. So this is the particular thing that we are trying to detect. So here's what it looks like. So if you look at the Einstein radius of this black hole, That's what is depicted here. And then the source can be passing anywhere in these locations along the Einstein radius or along the circle with the radius of the Einstein radius. And then you see that the magnification that the star achieves, that shows these typical light curves, right? So depending upon how far you are to the center of the black hole, if you go very close, you reach very high magnifications. If you are further away, then your magnifications become smaller and smaller. Okay? So the typical time scale of these light curves are of the order of the Einstein time, which is the physical scale of the Einstein angle. So it's the distance to the lens times the angle divided by the perpendicular velocity or the on-sky velocity of the source. So in order to do this microlensing, what we were using is a fantastic telescope. It's called the Subaru telescope. It's an 8.2 meter class telescope. And around 2014, this particular telescope was also equipped with a huge camera shown here, the hyper Suprime-cam. You can see how big it is. And the unique thing about this camera is that it has a really wide field of view, right? So 1.75 square degrees, about 9 times the size of the full moon. And so this gives, this is like the best telescope which has a wide field of view as well as a big mirror, right? So a large collecting power. So that allows it to see fainter sources, but also a large part of the sky. So this is a very unique capability which could make this kind of experiment possible. And so what happens is once you have great engineering advances, then you can actually make these observational advances as well. And that's what has happened in this particular case, right? So in addition to this, we also need a reservoir of lots and lots of stars, which can get microlensed. And in our case, Andromeda turned out to be a perfectly matched target. So Andromeda lies at a distance of around 770 kiloparsecs. It's perfect match for the field of view of HSC. So in one single field of view, you can see we can cover most of the disk of Andromeda. The distance modulus to Andromeda is about 24.4. And with a 90-second exposure, just 1.5 minutes, because of this really big mirror, 8.2 diameter mirror, it helps because then it allows you to reach magnitudes of about R of 25 or so. So this allows us to monitor the abundant population of DOS stars in the disk of the M31 for microlensing events. Of course, it also helps that there's a lot of dark matter in between us and M31, given the large distance, as well as the dark matter halos of the Milky Way, as well as M31. So that's what makes this particular experiment possible. So here's the experimental setup. We decided to take exposures of Andromeda, one after the other, on a single night. And we did the exposures for 90 seconds. There's a 30-second readout time, which means that we can get an image every 2 minutes on sky, right? So that's what we do. So the 2-minute cadence, it allows us to also probe the light curve timescales ranging from few minutes to few hours, right? So we have the entire night about 7 hours with a cadence of 2 minutes, right? So the upper limit on the primordial black hole masses that we can probe, it comes from the fact that we have 7 hours accessible to observations. If your primordial black hole is large, then the Einstein radius is large, and the time scale for your light curve also becomes large. And so if you have only 7 hours, then you are not able to get that particular light curve. On the other hand, if your primordial black hole is too small, then we have a 2-minute cadence. It should not happen that your light curve just misses the time which is in between. Right? So that is those are the limits that constrain our observations. Of course, one of the harder part of this observation is that each pixel of the image will have light from multiple stars. And so it is impossible to resolve all the stars that HSC can monitor. So we are in the pixel lensing regime. It's not like we can go ahead and look at each and every star and see whether it is its light coming from this star is fluctuating or not, right? So given the size of the PSF as well, there will be lots and lots of overlap between different stars. Okay. So it's a difficult kind of observation, but that's what we have done. We just keep on taking images, right, one after the other. Nature was very kind at that time, and the seeing conditions on the mountain were excellent. And so that allowed us to conduct these beautiful observations. We got about 188 exposures, as you said. So one of the first calculations that you do on back of an envelope is to calculate what is the optical depth for the primordial black hole microlensing events. So in order to do this, what you have to do is very simple. You're here on the Earth, and there's a star in Andromeda. And what you want to know is if there is a black hole here, or what is the probability that there is a black hole which lies in this particular volume, such that it can microlens this particular star, right? So the idea is very simple. In order to calculate the optical depth, you take the number density, you multiply it by the cross section. Here it's nothing but the Einstein angle, so it's just a circle with certain Einstein angle, right? And then you integrate over the entire line of sight, right? So this is a very simplified calculation. And because the mass of the dark matter goes in the denominator when you look at the number density, while if you look at the cross section, there is a theta e square. And so there is a square root of mass here. And so the mass just cancels out. So the optical depth does not have any dependence on the primordial black hole mass. So here's what the optical depth looks like as a function of distance from us. So initially the optical depth increases just because you're looking at the density of the Milky Way itself, and then it kind of flattens, and then it starts to increase right at the end, just as you start to enter the M31 halo. Okay, so the main thing to take away is the optical depth is about 10 to the minus 6. So if you have 10 to the 6 stars, on average, one of them will get lensed. Right? Thankfully, Andromeda has many, many stars, and so we are basically set, right? We were expecting of the order of hundreds to thousands of events to be seen with this particular observation. Okay. Of course, there's nuance to this, and that nuance is the following. It's not just worth calculating what the optical depths are, but you have to make sure that when the lensing happens, you can actually detect the light curve, right? And so what you need to work out is what are the expected event rates with a given time scale for the light curve, right? So here, the light curve is characterized by the time scale of the full width half maximum of the light curve. And what you see are these different curves here. So now you see that there's a breakdown in terms of the independence of mass. You see that if you have massive primordial black holes, then this is what the event rate looks like. While if you have lesser and lesser massive black holes, then the event rates look a little bit different, right? And so you can also see that higher mass primordial black holes, they will give you events which are peaked at a larger time scale for the full width half maximum. And if you go to smaller and smaller black holes, then they are peaked at lower and lower time scales. Of course, in order to calculate these expected event rates, we have to average over all possible velocities of the dark matter particles, all possible impact parameters that they can have given a source, and then the different distances at which they could be. So all those integrations, they go around when we do these particular calculations, the details of which you can find, of course, in the paper. So then you can calculate what is the total number of events that are expected. So this is then related to what is the fraction of primordial black holes which make up dark matter. So that's here. You have to integrate over all different times of light curve timescales, right? And then because this is the number of events per star, you also have to integrate over the different magnitudes that each of your star can have, right? So some stars are faint, some stars are bright. So if a fainter star gets magnified by a little bit, it may be very hard to detect. But if a brighter star is getting magnified, it might be easier to detect, and so on and so forth. So those kind of things also need to be put in order to calculate what is the total number of expected events that you will see. In addition to that, as I mentioned, there's also an efficiency factor of our detection itself, whether we are able to detect that light curve. If we just put it in the data, can we get it or not, right? So these are this is the main equation that goes in. And so of interest is this quantity. So of interest is this particular quantity. Right, so what happens is we are going to observe what is the number of events that we see. So that this particular thing can be observed. This quantity is something that comes from theory. So these are the curves that you can see here. Then this is the number of objects of different magnitudes. So what are the number of stars as a function of magnitude? So this comes from observations, either from HSC or from the HST observations of Andromeda. And then this particular piece of it, it comes from simulation. So we can actually put in a fake light curves of microlensing events and then ask whether our pipeline to detect those microlensing events, can it find these events or not, right? So these are these different pieces. And then I will go through some of these pieces one by one. So the first part is, okay, finding these particular events. And so the way to find these events is the following. We have taken multiple images of Andromeda. So you can see one image, another image here. And we want to find out whether one of these many, many peaks that you see here has changed in its flux or not. And you can see there's a lot of confusion. You don't know where each of these stars begin. Some of these peaks are very easy to understand. Some of them are just smudges around here, right? And so what we do is we take the best seeing image, which you can see here. And then there is a target image, which we want to see whether there have been changes which have happened in the fluxes of stars from this to this. And so we do a subtraction of these two images, and then we get a difference image. Now, of course, we cannot do a naive subtraction because if you look at these images, it is very clear that this reference image was taken at a time when the seeing was extremely good, while the target image is from a time when the seeing was a little bit bad. And so when you do a difference, you will not, if you do a naive difference, it will not be correct. You will see all sorts of donuts which starts to pop up in your difference image. So in order to do this, you have to account for the variation of atmospheric conditions and then perform the difference imaging. So that's what we do. And when you do it in the proper manner, this is what you get. You can see that there's a star which pops up. And I think it was fainter in the reference image than in the target image, and that's why it pops up as a black spot here. And so then we can make a catalog of these events which pop up in the difference images and start to make their light curves. So that's what we have done. So we can find many, many different kinds of objects which are quite interesting. So for example, this A image, A light curve that you see here, there was something which like flared up for a few minutes and then just went down. The flaring happened for where the star brightened by like at least a magnitude or a magnitude and a half, and then it started to decay. So this is like a candidate stellar flare. These are contact binaries that we saw. There are events when there was a star which had a flux of a magnitude of 22, and then it suddenly used to disappear for a certain while, very small amount of time, and then it comes back again disappears, comes back again disappears, and so on. So this is a candidate white dwarf, brown dwarf binary, and so on. So there were a number of these kind of light curves which popped up. We had to weed out these curves which did not look like microlensing, and then visually inspect things which looked like microlensing. There were some imposters as well. So for example, there are asteroids within our own solar system, which when they go across the disk of the Andromeda, then you start to pick up these asteroids as well. They are not doing any microlensing whatsoever, but these asteroids, they are like bright objects. And if you just try to work out what is the light curve at this point, then you see that it looks like a microlensing light curve as well. So we had to weed out all of these kind of imposters. Other kind of imposters are bright spikes or spikes around bright stars. So we had to remove them after careful visual inspection. And all that survived all these cuts that we did was a single candidate event. So here's what you can see. These are counts in the eye difference image as a function of time. You can see that it roughly looks like a microlensing light curve. Here's the reference, lots and lots of stars here. Here's the target image. You can see something in the difference. And if you try to fit by a PSF model, you can see that nothing survives, right? So this is consistent with something getting microlens, or maybe something which popped up, right? So we don't know. This is a magnitude 24.5 star, which brightened up for a little while, and then it went down. We have checked in archival observations and the observations that we have carried later on, whether this kind of star or whether this star had flared up as well, but we have not found any evidence so far. So then the last two pieces of it is the number of monitored stars. We looked at our HSC images, we looked at the Andromeda images from the Hubble Space Telescope, and we tried to work out what is the surface density of stars that we find. These are the kind of results. They match basically right on top. But as you go further and further, fainter events, then fainter stars, then HSC is not able to find some of these fainter stars, but HST can find them. Of course, they do exist. So if they are microlensed, HSC would still be able to find them, right? So we had the potential to monitor a total of about 10 to the 8 stars as inferred from the HST counts. We did a lot of efficiency calculations as well, but let me just go to the final results that we got, right? So this was one single night of Subaru data. And I had shown you where things stood for the primordial black hole abundance plot as a function of mass before our observations, and this is what you get after our observations, right? So this is the solid, the dashed curves that you see here. These are the limits that we can put. Whether we account for the one candidate event that we found or not, it doesn't matter much. But these are the kind of limits that we get. Okay. So initially, when we put out the paper on the archive, we had shown this dashed line, which was quite exciting. We could even rule out things even in this particular window. And that is when we had not accounted for two very important effects. One is that the sizes of stars in Andromeda, they are finite, right? And so we cannot treat them as point sources. That's what we were doing previously when we first put out the results on the archive. And then the second effect that we were ignoring is the wave effect, right? So our observations were done in a certain band. There's a wavelength of light that corresponds to this particular band. And so if your primordial black holes have Schwarzschild radii, which are smaller than the wavelength of that light, then you are not able to probe these black holes. So this was kindly pointed out to, the wave effect part was pointed out to us by Nick Kaiser. I had been going back and forth about the finite source size effect as well. And when we took into account both of this effect, most of it is just the finite source size effect, which just cuts out things at this location. Once we account for both the finite source size effect and the wave effect, it doesn't change much. But this is the final constraint that we have. Right? So in the end,
about 2 minutes.
Yeah. That's right on time. So this is my last slide. I wanted to end with a future outlook as to where these observations stand. So this is the M31 constraint, the 95% limit, as I mentioned. What we are doing next is to increase the number of nights. That's the simplest way in which we can push down this limit even further. Going from 10 to the minus 2, we can then go to 10 to the minus 3. The reason why it's important is because there are many different models which can have a power spectrum, which can have a mass spectrum, right? And so if they have a mass spectrum, then some of these primordial black holes can cut into our limits and so on. So it is important to increase the number of nights so that you can go down. The second thing that we are doing is, as I said, this limit is governed by the fact that we had only a single night and we did not do a long-term monitoring. So we are also now doing a long-term monitoring, which will allow us to extend these constraints even further beyond, even in the ranges where LIGO's black holes exist, right? So we are trying to do a long-term monitoring campaign, which will allow us to get some constraints here. And lastly, but most importantly, we are also trying to close the window on the left-hand side of this And this might be possible using old ideas in the 1990s, which we are now trying to revive as well, using something called parallax microlensing of gamma ray bursts. So one of the students here at IUCA is working on this particular thing. Priyanka Gowde, she is also in the audience here. So these are the ways in which we are trying to attack this problem. It's interesting to have theories. Of course, all these observations are incredibly difficult, but we are trying our best to make sure that we can provide some of these constraints. So with that, I would end the talk and take some questions. Thanks.
Thank you, Surhud. It's a very exciting result. We have a few questions. One is from Swagat. What are the best guesses for your single event?
That's great. So we don't know. It would be really exciting if it is a real primordial black hole. What I can tell you is what we have done, right? So what we have done is we said that, okay, maybe it is some kind of a variable star, and then it pops up every few hours. And so what we have done is we have to try to rule out what is the periodicity of this event by looking at what are the different epochs at which we have data from M31, which is available, right? And so far, it has not come up again, right? So it would be really exciting if this was really a primordial black hole, but then it is really hard to prove as well, right? And in terms of masses and so on, it's also very hard because it depends upon where exactly the primordial black hole was and so on and so forth. So we can give some statistical guesses as to if there was a compact object which lensed it, then where it should be and what its mass should be. But these will still be just probability distributions.
So there is no way you can look at this would not come back, right, in any reasonable time?
Well, there are lots and lots of stars. So it depends upon what exactly were the impact parameters, the velocities, and so on. So one will have to work that out.
Yeah.
Yeah.
So a couple of people have asked this question, Koushik and Kristen Bynes. Is it possible to move your constraints to the lower masses, for example, by looking at a more distant galaxy?
No, so I think as I explained, part of these things are also related to the wave effects, right? And so we are right at the limit of the wave effects at that particular stage. And so we need to go into bands where the wavelengths are smaller, and that's what will help us. Or these different ideas like parallax microlensing, where you have multiple satellites which are observing, say, a gamma ray burst from different locations. And then one of them will have the impact parameters for these two satellites will be different. And so they will see different kinds of light curves. So that's what we are trying to estimate and trying to work with experimentalists who may have such satellites in order to then try to get some limits there.
Yeah. So Suchetana Chatterjee has a couple of questions. Maybe Suchetana, you can ask them yourself.
Hello, Surhud, can you hear me?
Yes, I can.
Yeah, so I think the first one was about when you calculate the number of events, right? Yeah. You showed. Can you go to that equation, please? Yeah. So there are all these components that get into your integral. Yes, like you said, this comes from theory, this comes from observations, etc. Yeah, like what's the number as a function of magnitude and all that.
Yeah.
So my question is that in all those three entities, there are definitely some kind of uncertainties.
Yeah.
How does that relate to either the events that you observe? I mean, the error or the uncertainties on these entities.
Right.
How is that being incorporated about the number of events that you see? That's the first one. And the second one, you're talking about a line of sight, right? And I mean, that there is a PBH, or there's this PBH, the light goes, this is a line of sight thing. Yeah. So there can be other sources that causes microlensing. So how do you understand that it's coming from PBH?
Right. So it is very difficult to say. Like you just require a compact mass, right? And that's it. That's what can do this. Of course, the mass has to be small, just because I mean, um, uh, the light curve timescales give us the a rough idea of the mass, as you can see from the left-hand curve, right? And so the reason why we can be sure that there's not much baryonic matter out there is just because the lensing geometry will require you to have something roughly in between where Andromeda is and where you are, right? And so geometry wise, you would expect it at distances of order of hundreds of kiloparsecs. So 100 kiloparsecs, that's what I mean, we integrate over the entire line of sight, but that's roughly where we expect just from the geometry itself. Now, let's come back to your question about the uncertainties. One of the biggest uncertainties that people usually use is in these observations of the number counts of how many stars that we are going to use, and say whether they are going to be lensed or not, right? So if you use the HSC detected peaks, and as I said, the detected number of detected peaks is definitely a conservative assumption compared to whether you use the peaks from, as have been seen in HST, which is the Hubble Space Telescope, then you see that there is a big difference in the number, right? So there's like a factor of 10 difference. So you can change the limits that are shown by a factor of 10 if you use the HST versus the HSC detected peaks, okay? And so that's something that we mentioned clearly in the paper as well. And this particular constraint uses the HST because we know that they exist. It's not like if you don't see them with HSC or can't resolve them with HSC, it doesn't mean that they don't exist, right? And that's why when we gave the constraints, we used the HST peaks. But if you wanted to use the peaks which are detected only by Subaru HSC, just to try to be conservative, then you will have a line which is factor 10 less stringent than what you see here.
Okay, thank you so much.
Yeah, so those are the main uncertainties. And then, of course, there's the statistical uncertainty that we have seen only one event.
Yes, so that stays.
That stays. Right.
Thank you, Surhud.
Yeah, thanks.
Thank you, Surhud. So because of the limitation in time, we are delayed by 10 minutes already.
Sure. Yeah.
I would like to close the session now.
Yeah. No
so let us thank all the speakers for giving wonderful talks and keeping with the time limit. Thank you all.